All right, so next we're ready to tackle, this is going to be section 6.4, so we're going to talk about the gamma function, so the gamma function and other special functions. Okay, so we'll talk about some actual special functions that are defined via solutions of ODEs. And we're going to start with the gamma function. The gamma function is defined as follows. So it's defined as so this is a capital Greek capital G, it's a gamma. So this is defined as the integral from 0 to infinity. So integral from 0 to infinity of e to the minus t, t to the x minus 1 dt. And what we want to do is we want to talk about some values that this gamma function is going to give us. I just want to point out that this function, gamma of x, converges in the Calc2 sense that it's an improper integral, so the improper integral converges if x is greater than 0. Okay. If x is less than or equal to 1, so I just want to point out why this restriction is here. If x is less than or equal to 1, in other words, if x is, say, 1/2, then the trouble point is actually going to be 0. So if x is 1/2, this is going to be e to the minus t times t to the negative 1/2. And this e to the minus t is going to be basically negligible if t is near 0, right? That's basically going to be 1 if t is small. But this is t to the negative 1/2. And so if you remember the integral of, I guess I'm not going to write it, but the integral of t to the p, if you integrate from t going from 0 to 1, that converges as long as p is bigger than negative 1. So here we want our exponent to be bigger than negative 1. That means that x has to be positive. Okay, and if x is greater than or equal to 1, then the problem is going to be infinity, right? Because you're going to have, say, like t squared over e to the t. But it turns out the e to the t, or e to the negative t rather, goes to 0 so much faster than any polynomial that you get convergence. Everything's fine. So the gamma function converges for all x greater than 0. And what I want to do is I want to find a few values. So I want to first compute gamma of 1. Okay, so I want to compute gamma of 1. And gamma of 1 is just going to be the integral from 0 to infinity, e to the minus t dt. And it turns out that this is going to be, if I want to do this, let me do this completely the right way first. So this is the limit as t goes to infinity, integral from 0 to t. Actually, I shouldn't use t, sorry. Let's say b. So this is the limit as b goes to infinity, integral from 0 to b, e to the negative t dt. And now this is just a limit of a normal integral over a finite interval. So this is going to be negative e to the negative t from 0 to b. And then that's going to be, let's see, negative e to the negative b plus 1. And negative e to the negative b is going to go to 0. So that means that this whole limit will be 1. So gamma of 1 is 1. And then what I want to do is I actually want to show you a recurrence here, gamma of x plus 1. And gamma of x plus 1 is going to be the integral from 0 to infinity, e to the negative t, t to the, well, if we replace the x with x plus 1, this becomes t to the x dt. Okay, and so that's the integral that we're going to have to deal with. And what we're going to do is we're going to do an integration by parts. Remember that our formula for integration by parts, I just always like to write this part down, but our formula for integration by parts is that we have the integral of f, let's do f prime times g. So that's fg minus the integral of fg prime. And so, the thing that we need to decide is what are we going to differentiate and what are we going to try and integrate. And I want to differentiate t to the x, okay, because that'll make this a little bit easier to deal with. So I'm going to let our g I'm going to let our g be t to the x. Remember that this is g of t. This is a function of t. X is some fixed value like 5. Right? So it's like integrating t to the 5. And so g is going to become, so if g of t is t to the x, then g prime is x t to the x minus 1. Again, our primes are kind of hiding the fact that we're differentiating with respect to t. All right, and then that means that f prime of t is going to be the other thing. It's going to be the e to the negative t, and that means that f is negative e to the negative t. And so altogether what's going to happen is that this is going to become, let's see, the integral of f times g, so that's negative t to the x e to the negative t. We're going to go from 0 to infinity, minus the integral, so minus the integral of fg prime, which is going to be negative e to the negative t, and then g prime is x t to the x minus 1 dt. Again, this is not a substitution, so the bounds stay the same. And again, let me just kind of wall off our substitution that we're making here. So this is going to be our new integral that we'll have to deal with. And again, you could write this, if you really want, you could write this as the limit as, say, b goes to infinity of negative t to the x e to the negative t evaluated from 0 to b. And then let's simplify this other part. Notice that our integral is with respect to t. Okay, so we have a dt. That means that x is a constant, and therefore this x can be brought out. The negatives are going to make a positive, and if I do both of those changes, I end up with plus x times the integral from 0 to infinity, e to the negative t times t to the x minus 1 dt. And so the first bit is going to be this limit as b goes to infinity. Let's see, if I plug in b, you're going to get negative b to the x, e to the negative b. And if you plug in t equals 0, you'll get 0. And it turns out for any fixed value of x, this first part is also going to be 0. Okay, so this is going to go to 0. This is already equal to 0. And so this first limit is going to be 0. Okay, and then the last thing that we have to do is just recognize what is this integral. Right, so we need to think about what is that integral. And it turns out that that's going to be, that integral is just gamma of x. So just in conclusion, let's see what we've shown here. We know that, so what we just said was that gamma of x plus 1 is going to be x times gamma of x. And we know that gamma of 1 is 1. So if we think about gamma of, say, 5, that's going to be 4 gamma of 4. And now gamma of 4 is going to be 3 gamma of 3. And gamma of 3 is 2 gamma of 2. We're almost done. Gamma of 2 is going to be 1 times gamma of 1. And that's gamma of 1 is just 1. So it turns out that gamma of 5 is 4 factorial. In general, gamma of n plus 1 is going to be n factorial for all integers. So for all integers n greater than or equal to 0. So even for 1, gamma of 1, this 1 that we get here for gamma of 1, we can think of as 0 factorial. Okay, and that is the gamma function. We have one last thing to evaluate, and that's gamma of 1/2. Okay, and so gamma of 1/2, what we're going to do there, and we need to be a little bit clever here, gamma of 1/2, really these half integer values are going to be something that will be very useful for us. But gamma of 1/2, let's just plug everything in. we're going to get the integral from 0 to infinity, e to the minus t to the 1/2 minus 1 dt. So in other words, this is the integral from 0 to infinity, e to the negative t to the negative 1/2 dt. And what we're going to do is we're going to substitute. I'm going to let u be, let's let u be t to the 1/2. In other words, t is u squared. And then that would mean that, there's a few different ways to do this, but that would mean that du is going to be 1/2 t to the negative 1/2 dt, or 2 du is equal to t to the negative 1/2 dt. And so if we take that, if we take these values and plug them in, what we're going to get is that this is going to become the integral. We'll have to change our bounds, but we'll get the integral from e to the negative t, so that's e to the negative u squared, t to the negative 1/2 dt, very nicely just becomes 2 du. So I'm going to put the 2 out front. And then I'm going to think about what happens to u as t goes to 0 into infinity. So really, if what I want to do is I want to think about u, and I want to think about what happens as t goes to 0, and what happens as t goes to infinity. And this is t to the 1/2, just square root of t. So as t goes to 0, this is 0, and as t goes to 1/2, this still goes to infinity. So the bounds actually stay the same. And then this is the integral somehow that we need to wrestle with, the integral from 0 to infinity, e to the negative u squared du. This is a classic integral. It does not have an elementary solution, so there's no nice thing that we can do here as far as evaluating this integral explicitly as a function. But what I want to do is I want to show you one of my favorite tricks, basically my favorite trick in all of calculus here. We have enough to be able to actually solve this integral. So I'm going to leave a little bit of space here and come back. And so we'll figure out exactly what gamma of 1/2 is. But we really need to wrestle with what's the integral from 0 to infinity, e to the negative u squared du. So I'm going to call this integral I. And what I'm going to do is, actually, I'm going to change my u's to x's, because it doesn't matter. X or u is just a dummy variable, but this will just give us a little bit of geometric intuition here. What I'm actually going to compute is I squared. And I want to just first point out that I has to be positive, because we're integrating a function that's positive over some interval, right? So if we integrate a positive function, right, if you have some integral of whatever it is of a positive function, that area, that integral is going to be that positive area. Okay, so the integral is going to be positive. It turns out I squared is much easier to evaluate than I. So I squared, I'm going to write, this is going to be a little bit silly, but I'm going to write this as the integral of e to the negative x squared dx times the integral from 0 to infinity e to the negative y squared dy. Both of these integrals represent the same, both of those terms are the same integral, just with different variables. So this really is I squared. The reason for writing it in terms of two integrals is that now I can combine this into a double integral. This is the integral from 0 to infinity, and from 0 to infinity, e to the negative x squared, e to the negative y squared, dx dy. This does not look any better, but it turns out it really is. This is going to be the integral from 0 to infinity, integral from 0 to infinity, e to the negative quantity x squared plus y squared, right? Because you add the exponents, you got e to the negative x squared minus y squared. That's basically what you get if you were to multiply them. You would add the exponents and then factor out the minus, and that makes that a plus. So you got e to the negative quantity x squared plus y squared dx dy. And this integral is just absolutely shouting out for you to use polar coordinates, right? You have an x squared plus y squared. We're integrating over the region where x and y are greater than or equal to 0. So we're integrating over the first quadrant here. And what we're going to do is we're going to let r squared be x squared plus y squared. And we know that dx dy is going to be r dr d theta. And so we just have to think about what are our, what's this integral going to become? So this is e to the negative r squared. Dx dy is our r dr d theta. That's from the Jacobian of the transformation that we make, right? So classic polar coordinates. And then r is going to be the radius of our circle. So it's going to go from 0 to infinity, right? So r is going to go from 0 to infinity. And theta is going to be the angle that we make, and it's going to go from 0 to pi over 2. That's it, because we're just talking about the first quadrant. So from 0 to pi over 2. And now this is a straightforward integral to evaluate. I actually want to point out that the integral from d theta from 0 to pi over 2 is just going to give us pi over 2. Right? This is really, you can now separate the integral. This is the integral of d theta from 0 to pi over 2 times the integral from 0 to infinity e to the negative r squared r dr d theta. So this is pi over 2. And then I want to think about what is this integral going to become, the second integral. And so to do that second integral, we're going to substitute u as r squared. Du is going to be 2r dr. And I wrote d theta twice. I didn't mean to do that. So we get du is 2r dr. That means 1/2 du is r dr. And then if r goes from 0 to infinity, then u also goes from 0 to infinity. So it's going to be 2 times the integral from 0 to infinity e to the negative u du. Okay, du. So our, there we go, du. And I wrote a 2 in front, which I didn't mean. The 2 should really be a 1/2. Because our r dr should be 1/2 du. So it should be a 1/2 du. All right. And that's perfect. This is going to be the integral. So this is pi over 4 times the integral of e to the minus u from 0 to infinity. And we've already computed that. That's going to be negative e to the negative u from 0 to infinity. When u goes to infinity, we get 0. Minus, let's see, negative e to the negative u. When u is 0, we get minus 1. And altogether, this integral is going to be pi over 4. So notice that we found this area even without finding an antiderivative of e to the negative x squared. Okay, but this integral is pi over 4. And so now what we're going to do, is we're going to remember that this was I squared. And so I squared was pi over 4. I made a point to mention that I had to be positive, so that means that I is really going to be 1/2 times the square root of pi. Okay, so that's really what it is. We know that we get the positive square root because we said that the original value was positive. Okay, so I is going to be 1/2 square root of pi. And then that means that we're done. This integral that we're looking at was 1/2 square root of pi. And so it turns out that gamma of 1/2 is square root of pi. Okay, so gamma of 1/2 is square root of pi. Okay, that's the other big kind of family of values that we're going to worry about for the gamma function. And by family, what I mean is the half integers. So if you were to have gamma of 5/2, that would be 3/2, gamma of 3/2. Gamma of 3/2 is 1/2, gamma of 1/2. So altogether, that would be 3/4 square root of pi. Right, so that tells you how to find gamma for all the integers plus 1/2. All right, so that's the gamma function that'll be necessary for what we're going to do next.